All right, so I apparently stirred a discussion about how bad the school's Wi-Fi is. And now let's get back to focus. Let's focus. And I'm going to go through these homework problems with you. And I want to say again, my plan is I am going to Wednesday night, so that's tomorrow night, 7 to 8 p.m. I'm going to send out a link on Google Classroom. And if you need me to talk you through Polar from more of a beginning, I can do that, because apparently a lot of people missed learning Polar due to the spring COVID. And I just did not think about that for some silly reason. Anyway, here we go. Reading the words is hugely important. Now, I taught you about slope, which is dy over dx, but not every derivative is slope. You have to read who are you taking the derivative of, and with respect to what variable. So you want to read, what is the instantaneous rate of change of? Rate of change of. R is the function we're taking the derivative of. And then with respect to theta, you've got to read those things very carefully, especially on the BC exam. So write down what it is that it's asking you to find the derivative of, and then take a look at what you have. This isn't asking you for dy over dx. This is asking you for the rate of change of r with respect to theta, and it happens to be written in terms of theta. You're literally just taking a derivative like normal. But I know that after all that time spent on the slope formula, you start thinking that the derivative is more complicated than that. So now you are forewarned of how the AP test will kind of go all over the place. So we are going to quotient rule, and I will take you through it. That means we get loaded on math with an A, math is what we get loaded on. So low D, high, minus high D low, square the bottom, and away we go. Now it wants the instantaneous rate of change when theta is 2. So now I need to plug 2 into all my thetas and see which one it is. So plugging into 2 squared plus 1 gives me 5. And then I have a, let's see, I've got 20 times 4, and then 5 squared. So 50 minus 80 over 25. And that's going to reduce to negative 6 over 5. And then that problem is done. Okay, number 2. Now number 2 is being vague with me. It's saying, hey, there's a function, r equals f of theta. And then it says, okay, if the tangent line to the polar curve at, now this is not giving you the function f of theta. This is just telling you the input variable location. So it's basically like being given x with regular functions, but it's theta this time. And you are told that the tangent line at that angle is horizontal. So when I have a horizontal tangent line, I do want to think about slope. And slope is always dy over dx. If I'm working with polar, I want to realize that my slope is actually dy d theta over dx d theta. Now, a horizontal tangent line will happen when the numerator is 0. So that's going to be my focus, is I need dy d theta to equal 0. And everyone's paying attention? Everyone's paying attention? Okay, all right. Now, in order to get dy d theta, I have to first remember what is y in terms of theta. And do you guys remember off the top of your head? Mm-hmm. And if you don't remember, draw the triangle. Here's an xy plane. Here's a point in quadrant 1. That point has an x and a y coordinate. The polar point has a radius and an angle. Through that triangle, you can figure out your SOHCAHTOA, and then from there you can realize that sine of theta is opposite over hypotenuse. Opposite over hypotenuse. All right. Now, they didn't give me the function. So you're probably at first feeling like, oh no, I don't know what's going to happen. I'm scared. Whatever you do, your biggest enemy on the AP test is panic. Here's what I guarantee you. Most of the problems you're going to know how to do. They may not look like you know what to do, but you're just going to calmly think, what do I know? What can I do? How do I do it? And there will be an occasional problem that you might get really frustrated with. In that case, if it's multiple choice, make a guess, move to the next problem, forget about it, put a star. If you've got time, come back to it. But know that you will understand most problems, just not off the bat. You're going to have to play with it a little bit. Pretend you're a cat and this is a mouse. Have you ever watched a cat play with a mouse before eating it? It's terrifying. But pretend that you're a cat, you own this test, and this is some silly mouse trying to get away from you, but you know you're going to own it. You are. It's going to try to get away, but you can grab its tail. Okay, let's not get too... Maybe. Okay. We are focused on this. dy d theta is equal to 0. What do I have? I have this. Looking at the possible answers, I see, oh, it looks like I need to just go into product rule, even though I don't know f of theta. So I've got my first function. Let me zoom in. I have my first function, and I have my second function. And product rule, here we go. dy d theta is keep one, multiply by the derivative of the other, plus swap who you're taking the derivative for and who you're keeping as is. Now they did give me an angle. They gave me the angle when theta is pi over 3. So now I'm going to find dy d theta at theta equals pi over 3. So I plug in pi over 3, and I keep plugging in pi over 3, and I keep plugging in pi over 3, and again. Now at this point, when I look at the answers, I see, oh, okay, it's one of these two, but I primarily need to get the correct answer to the unit circle's value of cosine of pi over 3 and the unit circle's value of sine of pi over 3. So now you're probably starting to feel comfortable, or maybe your unit circle bothers you. But with your unit circle, angle pi over 3 is when you cut into thirds. So you've got pi over 6, pi over 3, pi over 2. Keeping in mind that another way of cutting the unit circle is cutting it in half, so that you have pi over 4 as well. When you're looking at your pi over 3, it has an x-coordinate and a y-coordinate that you can base it on with respect to where the other points have x and y coordinates, because the special numbers go 1 over 2, root 2 over 2, root 3 over 2 for these numbers in here. And then it hits the x value of 1. For the y values, 1 over 2, root 2 over 2, and then root 3 over 2. So that gives me my x and my y coordinate. The x coordinate is the cosine, and the y coordinate is the sine. And now let's see which one matches that up. So I'm going to highlight the regular f of pi over 3, and now I can see that it's letter D. So the idea is you've got to go through these problems with kind of a calm, cool, collected, almost meditative state. And they do ask problems in strange ways, and it's just the way the testing goes. Now let's take a look at this and notice the graphing calculator symbol. So this is a calculator problem. They gave you the drawing of this curve. They told you that that drawing is between 0 and pi, and it's asking you to find the area of the region bounded by the curve and the x-axis. So you've got to remember, what is that formula? Can everyone just think in their head, what is the area formula for polar? And hopefully you just thought 1/2 r squared d theta. Then, if I'm going to find the area from 0 to pi, I just need to tell the angles to go from 0 to pi. And I've got my r. Now let me show you what you should be seeing. As theta turns from 0 to pi, draw spokes coming out of the origin. So that means angle 0, and just draw it from the pole over to the function. Then I'm going to draw from the pole straight line to the function, straight line to the function, straight line to the function. As I draw these, it's telling me what I'm actually finding the area of if I integrate this particular curve from 0 to pi. Drawing those helps a lot to just recognize what you are doing. At that point, you're going to plug this into your calculator. Know that you don't need to be in polar mode. In fact, I would recommend that you never go into polar mode during the AP exam or parametric mode. When you type in your integral, if you feel the need, you can just use the letter x wherever you have a theta. And then that's going to pop out one of these answers. Now, it helps to actually be thinking about, how do you think they're going to try and trick you? How do you guys think they will try to trick you? Yep. A lot of times people will forget the 1/2 with this area formula. So the theta looks like a 0. Or my theta looks like a 0? Or I don't know. But it can help a bit to be aware of what you think they might trick you on. If you realize that they're probably going to trick you with that, no, the 2 theta in the problem that kept. Oh, you mean like typing it wrong? Or having to deal with that in the calculator? So you should expect that the number that comes out of your calculator also has double it sitting around too. This is what should come out of your calculator. And notice that that doubled is also sitting there. What do you think is another common thing that they're going to assume? Some people are going to make this mistake. What is another big formula mistake? That squared thing. And by squaring that r, well, granted, it depends on the numbers you're working with, but if you were to look at what numbers you get if you forget that r squared, you'll probably get one of these. And then one of them is probably double the other as well, just to kind of test you. And I'm kind of seeing, oh, these two are double. So when you're taking the test, you don't want to do this. But while you're studying the problems before you take the test, this is a good thing to do. And recognize where they're trying to trick you. It just helps to come in with that mindset. That way, you realize what to be cautious about. And when it comes to area formulas, it's all about, do you have the correct basic formula? And then the other issue that sometimes pops up is, did you deal with the correct angles? Mm-hmm. For the AP exam, there will be 5. Yeah. Their problems that are 4 answers are ones that never made it to a test. The ones that have 5 answers are problems that were very likely on a previous AP exam. And you want to make sure that your angle is 0 to pi, creating that particular region. Okay. Next problem. Now, while we're working these problems, I am going to do more than you would necessarily do while you're on the problem. They give you the graph, so that's convenient. It looks like you can probably get one of these loops from 0 to pi, and then you can double that area to get the other round. So that's a possibility. If that is what is happening, then the formula is again 1/2 r squared. But if I only go from 0 to pi, then I'm going to double my area, and my r is sine squared theta. And then I look around and I see, oh, hey, probably that answer. But if you want to make sure that you're doing this correctly, it also helps to think about how this creates the graph itself. So you probably don't want to spend time doing what I am about to do while you're in the middle of multiple choice, but I want to strengthen your polar skills. So by strengthening your polar skills, what I do is I look at what's here and I just temporarily think, what if I had, I'm going to start with y equals sine x. And then I'm going to think, what does it mean if I square all those y values? So I'm starting with what I know coming in about sine. I know its graph goes, woo. Yes, I really need one of those little slide. Yeah. And I know that this is going to be 2 pi over here. I know this is going to be pi over here, 1, -1. Now, if I square the y values, what is that going to do? It'll force... Mm-hmm. So this negative is going to flip up. Squaring 1 keeps it at 1. The squaring of numbers that are between 0 and 1 technically make them smaller, but you're not going to worry too much about that because really you're trying to see where do loops occur. From what theta to what theta does the graph come out of the pole, and then where is it forced back in? So as I travel from 0 to pi, which would be traveling from here to here, I do create one loop. And that can make me feel much more secure about using this formula. Then, when I go from pi to 2 pi, I will have a positive r, creating another loop, which we see there. So I'm hoping that by doing this and translating it over to here, that's going to help you get a better feel for polar. And polar is so beautiful, and it's really, really convenient that we can use our Cartesian skills to translate with. And it's just, we should do so much more with polar graphing. But anyway, here's the next problem. And we want to read it carefully. R is a region in the first quadrant. It is bounded by R equals theta and theta equals k. For R equals theta, you want to think about what this is saying. As theta turns, so 0 is going to be here, and then I'm going to turn. And as I turn, I go farther down this line. So you want to imagine that you actually have a number line, 0, positive side, negative side, that is turning. And while it is turning, the input is just going, I'm radian 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, It's basically just heading out this way while it is turning. So it's going, I'm getting bigger, I'm getting bigger, I'm getting bigger, I'm getting bigger, and it is spiraling out. And now what I'm going to do is emphasize that this particular graph is the graph R equals theta. Now, the other one is theta equals k, and this is where you want to remember, if theta is a constant and that's all you have, then you're dealing with, first of all, if your radius is positive, just a ray coming out of the origin. If my r is positive, it will be just the ray. If r is allowed to be negative, then I will get a negative side and a full line. Now they are telling you that the region is bounded by those two curves. So you should be able to see now that this is the equation theta equals k. And they do tell you that k is somewhere between 0 and pi over 2. So you know that you're dealing with quadrant 1. It did say that. And if my k is going from 0 to pi over 2, then realize that that means I'm dealing with values of r that are also 0 to pi over 2. They are positive values. So it is just array because I'm only working with positive r. Now, when you get ready to set up an integral, you want to be thinking about how area is created with polar. Area is created by starting at angle 0, and I first go nowhere. Then theta turns a little bit in the positive direction, and I am following a particular function, until I reach this theta. So I am going to be turning from 0 to this angle, which happens to be theta equals k. And while I do that, I am only following this curve, who is r equals theta. Now, the formula for area is 1/2 r squared d theta. The function that I am following is r equals theta. This other border is just creating an angle border, not a function border. So that's like when we were doing rectangular. If you were told that you, say you were looking at a particular curve and it was bounded by, say, x equals 3, and you were looking at area in quadrant 1 bounded by this graph and x equals 3. The 3 only shows up as an endpoint of the integral. Only this curve becomes the integrand. So it's very similar to that. It's just, instead of being boundaried by vertical positions, you are boundaried by angles instead, coming out of that pole. So what do you do now? Well, if you look at the possibility of answers, you realize, oh great, I have to integrate by hand. So with respect to theta, the variable is theta, the function is theta squared with a 1/2 multiple. So integrating, I add 1 to the exponent and divide by that number. And I evaluate from theta equals 0 to theta equals k. When I plug in k, I will get k cubed over 6, and plugging in 0 will give me nothing. And now I've got an answer. You would not spend this much time on it. But I'm trying to also teach you polar while we're doing these problems, unfortunately. But we're getting there. Who gets distracted by noise? Is this just killing you? Okay. Is someone vacuuming? Oh, tennis? Oh my God. Oh dear. Distractions, distractions. And that's where learning to focus and focus your mind is so, so, so valuable. Okay. So focus our minds. Nothing exists other than math. Oh my gosh. If that were the case, then I wouldn't have to wear a mask and we could be closer together. Okay, sorry. Math. It's all that exists. Which of the following integrals represents the area enclosed by the smaller loop of the graph of this? Now, this is where it really would come in handy if you were more familiar with polar graphs. But that doesn't make this impossible if you don't know your polar graphs. What you want to remember or try to remember is if you see a sine or a cosine function and you notice that you have addition or subtraction, as long as that theta is not multiplied by a number, you have a limacon. And if the amplitude, if the amplitude of the graph is greater than the vertical shift of the graph, then you're going to have some of the graph go on both sides of the x-axis. And when I do sketch 1 plus 2 sine x, when y is equal to 0, that is when r is equal to 0. And those are the most important r values that I need to know. Now, you know your basic sine graph. Whee! Then we multiply by 2. Whee! And then we move everybody up 1 unit. Which means 3, and then up 1 unit 1, and up 1 unit -1. Whee! Whee! And you can see where it crosses the x-axis here. Now, I will tell you that this graph is much more meaningful than if you were looking at the polar graph. If it says enclosed by the smaller loop will be the smaller section that is cut off from the x-axis. So you need to figure out what are these theta values, because those are the angles you need to integrate between. Now, let's go back to the area formula is 1/2 r squared d theta. My r is 1 plus 2 sine theta. And I need to find now these two numbers, and I'll be having an integral. Now, looking at the possible answers, I can actually maybe save a little bit of time. But let's say you didn't have the answers and you needed to remember, how do I use my unit circle? So what you're going to do is start off, stop doing that to everyone. You're going to start off with, I need to know what makes r 0. You're solving a trig equation. First thing is, isolate the trig function, subtract 1, divide by 2, then unit circle. Sine are the y values, This y value is negative 1/2, so that is the first one down. And that takes us to pi plus pi over 6, as well as 2 pi minus pi over 6. So my integral will be correct if I do this, but that might not be the way the answer is given. But first thing is, are any of them given in that way? Yay! Look at that. Oh, nope, not that one. This one? Top one? There we go. Keep in mind, why are they trying to trick you? Look at these two. They both have the squared bit. And if you look at the angles, do you see how they are trying to trick you? Right. You want to, I would say that you would have an easier time with this problem in not mixing up the angles if you look at literally 7 pi over 6 to 11 pi over 6 will create that smaller loop. I have found it much easier to, I almost always set up my integrals by drawing the Cartesian graph. I rarely graph the whole polar graph to figure out where to put what angles I want to use. All right. Next problem. Don't panic. Don't panic. You have a graph. You have a table. Let's see what it says. Blah, 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 blah. Super important. Right Riemann sum. So what exactly is a right Riemann sum? A right Riemann sum means you are going, it was based on the idea of if I split the x-axis up into pieces, then for each interval of x, it is the right x value that determines the value of the function that I'm using. So what I'm going to say is I'm going to call this x sub 1. This is f of x sub 1. Now, when I translate that into polar, that means for every angle sweep, I want to take the last angle of the sweep, which means as theta goes from 0 to 1/4, which you don't have to know exactly where 1/4 radian is, just from angle 0 to some other angle, a right Riemann sum is going to use this value, that R value. Now, when you did right Riemann sums back in the day, you were just dealing with an integral that was literally just f of x times dx. And so you could take the height of that rectangle and multiply that by the width of that rectangle, and you've got area. But now the area formula isn't just height times width. The area formula is 1/2 r squared d theta. So delta theta. Now you are told 4 subintervals indicated by the data in the table. So now we're going to take a look at the data in the table is this delta theta is 1/4. Whoops, delta theta. This next delta theta is also 1/4. Oh, another 1/4. Oh, and another 1/4. Convenient. Every one of my delta thetas is 1/4. So that means the formula is going to turn into 1/8 times r squared for each area. And I'm using the rightmost r's. So my first area of a sector will end up being 1/8 times 4 squared. Second one, 1/8 times 3 squared. And then we find that it is this one. Now I want you to think about what are they definitely going to try to trick you on. I can see one thing that I know they will always try to trick you on when it gives you a right Riemann sum. If they give you a right or a left Riemann sum, I guarantee you with multiple choice, you're going to have one of the answers as a right, one of the answers as a left. So be careful with that issue more than anything else. Be careful with that issue. And you can see that it looks like what they've done is they've tried to trick you not only with the fact that this one is a left Riemann sum, but also if you look at these two, it's all about the formula. Whoever answers these two is thinking about it in the Cartesian format. The Cartesian format is just the value of the function times the delta x, because that's what this is giving. So if you're aware of that, you might see these and go, oh, that's where they're trying to trick me. Take those out of the game. You can always play the game of what isn't going to be the answer. And that gets, sadly, it gets a lot of people through multiple choice tests. So, number 8, the last problem. Now, all it says is there are 2 R values. It does not specify which graph is which, but the fact that you've got a 2 versus a 4 multiplying, you should see that this larger loop is going out further. In fact, it's going out to 4. And then this inner loop is the smaller one, the 2 sine squared. They additionally are telling you that we are working from 0 to pi. So it's immediately giving you the values of the endpoints of your integral. In fact, if you look at all your possibilities, they're all 0 to pi. So really it is focused on the area formula. Now we want the area of the region that is bounded between these 2 curves. If I'm bounded between them, then I'm looking at this region. And you want to think about how area is created with polar. So I'm going to start off with, if I integrate the function that goes further out, it's going to give me more area than I really want to get. But draw the spokes coming out of the pole, and you'll have a better feel for what the integral of 1/2 r squared d theta is giving you. It's giving you all of that. We need to take away from that this area. And to do that, we're going to integrate this r. But for the same angles and with the same formula of 1/2 r squared. So the easiest thing to do is put it into one integral, 1/2 r squared. Where that is now my r. Then if you look at your possibilities of your answers, you see that you need to do some algebra with this. So very carefully, 4 squared is 16, and then sine squared is sine to the 4th. Minus 2 squared is 4, sine squared. And don't forget that you've got a 1/2 out there as well. And how painful is it realizing that there are people who write the 1/2 over here and then forget it once they get to this point and put the wrong answer down. So being focused and really practice writing full lines. Always drop that thing, drop what's in front down before you start playing with the algebra, and you will avoid that kind of error. Just always try to drop the entire line down. It may be a lot to write, but it's worth it. 16 minus 4 is 12. 12 times 1/2 gives you 6. And there it is. Yay! Okay, we have a little bit of time. Now, first of all, everyone saw tonight's homework. It's 3 free response problems. It's going to challenge you. And I'm going to go over them with you tomorrow. Learn as much as you can through your mistakes. Learn through your mistakes. It's a fantastic way to learn. We've still got a few minutes left. So how about we do a little bit more? Talk about polar. And I feel like at this point, the best thing I can do to talk polar with you is to talk about the rotating line. Your rotating line has a positive side and a negative side. And basically, you've got some r equals f of theta. The value of r itself is just causing this to move along the line back and forth. But this is turning while you are going back and forth. Now, I remember when you guys were little, I would go to the science center and take someone else who was little. And they had those sand turning things where you had a brush and there was a wheel and there was sand, and you would try to draw in the sand while it did it. I tried over and over again to draw polar curves, and I can't tell you how hard it was, because I can't mimic how quickly this r is moving back and forth very well. But what I would do was I would turn the wheel and have it turning, and then with the brush, I would try to move it just back and forth and see if I could make polar graphs show up. I never did make them well because it's really hard to mimic the fact that the speed I am moving changes constantly. And it's very hard for us as humans to mimic a quick speed change. You know? But if you think about that is how polar is created, that can help you tremendously. It's like a wheel that is turning and you're just going back and forth on a line while that wheel turns, and that creates a drawing on that wheel. So if you ever played with that when you were a kid, put yourself back into that position where you made it spin and you're just having fun with the little brush. That's polar graphing. So you want to imagine, hi. Okay. So you want to imagine this turning, and while it is turning, if you have R increasing, then maybe it's only here, then it's further, then it's further. Do you see the spiral nature in that? That if while it turns, you are literally just going, but if you are dealing with while theta turns, your R is actually decreasing, then maybe your R is out here, and then your R is getting closer to the pole, and you can see that inward going spiral. Us drawing it is very difficult. We're not going to draw it perfect. You just need to realize that if theta turns and R increases, you spiral outward. If while theta turns, your R is decreasing, you're actually spiraling inward. And then the biggest issue is knowing that loops are created between zero values of R. So a lot of times your focus is really at what angle does R go from 0 into positive or negative numbers? And then at what angle does it get sucked back in? Those are the angles you want to integrate between when you're trying to find area. When it comes to derivatives, you have to ask yourself every single time, what function is it asking me to take the derivative of, and with respect to what variable? Because sometimes they are going to ask you for just dy d theta. Sometimes they're going to ask you for just dx d theta. Sometimes they're going to ask you for dr d theta. And other times they're going to ask you for slope dy dx. It's specifically when they ask you for slope that you have to do the full gamut of what is y and what is x in terms of theta. What is y in terms of theta? Or in terms of both? R sine theta, and x is r cosine theta. Then with, if you just need to find dy d theta, you just need to come up with what is y in that triangle formula. If it's just dx d theta, you just need to come up with what is x in that formula. But you saw from those multiple choice problems that sometimes they just flat out ask you for dr d theta, and you're not using these formulas at all, so don't feel like you have to always use them. First ask, who am I taking the derivative of? and with respect to what variable also. And then if you write that down, you can then go from there and figure out what you're working with. Okay, bingo. So have a great day. Enjoy your last class. And I'll put up on Google Classroom a reminder that we're going to focus on Polar for Wednesday night, 7 to 8. And if you have questions, ask them during that time. But I do see that we need that extra bit. I need to stop recording.